Swayam Prabha. Digital India. Educated India.
Earlier in the course, we have looked at modeling and simplified representations of complicated circuits. The earliest example was if you have a network of resistors, then if you are given two terminals, across those two terminals, you can represent the entire complicated circuit by a single resistor. The idea is that if you put this complicated circuit in a box and then bring out only these two terminals, it's indistinguishable. You cannot figure out the difference between this box and another box which contains only a single resistor of the equivalent value and whose two terminals are brought out. Okay. So, that is what is meant by this resistor is equivalent to that complicated circuit at those two terminals. Okay. So, by studying the electrical behavior at those two terminals, you cannot distinguish between the two. Then later on we saw examples, and this business of equivalent resistance holds for any linear circuit, not just a network of resistors, but also a network of resistors and linear control sources. Okay. Later, we also saw Thevenin and Norton equivalents, which are equivalents of a circuit containing independent sources and linear components. Okay. The entire circuit, however complicated it is, can be modeled at those two terminals using a single voltage source and a single resistance in series, or a single current source and a single resistance in parallel. Okay. Now, in this unit, we will discuss two-port parameters, which is a way of extending this abstract representation of equivalent resistance to more than one pair of terminals. Okay. So, before we go into that, I will discuss some extreme cases and show you why many representations are necessary. Okay. We have different sets of parameters describing the same two-port. Why all of them are necessary, I will describe, because it turns out that in some extreme cases, some circuits can be represented only by one and not by others. Okay. Now, there are many circuits which can be represented equally well by all of them. I will show you with examples that in some cases, some of the parameters will be undefined. Okay. If you have a network containing resistors and linear control sources and a pair of terminals is brought out, then at these pair of terminals, it is equivalent to a single resistance. The resistance could be positive or negative. If this network consists only of physical resistors, then this resistance will also be positive. Otherwise, if it also contains control sources, it could be negative. Okay. And similarly, if we have independent sources, resistors and control sources, it is equivalent to having a voltage source in series with a resistance, which is also equivalent to a current source in parallel with a resistance. Okay. And by the way, instead of specifying the equivalent resistance in this particular case, I could also specify the equivalent conductance. Okay. Now, you may be wondering why so many alternatives are necessary. Okay. I will show you very simple examples where some of them are legitimately defined and the others are not. For instance, let us say that between 1 and 1 prime, there is a short circuit. Okay. Inside the circuit, somehow it could be a direct short circuit or it could be emulated using control sources, whatever it is. Then this can be legitimately represented by an equivalent resistance which is 0. Okay. On the other hand, if you calculate the equivalent conductance, it will be infinity. Now, infinity is not a useful quantity in the sense that you cannot make usual calculations that you do with finite numbers when you have infinities. Okay, 0 is okay, but infinity is not fine. When you have to manipulate infinities, sometimes what you have to do is to assume that that quantity is finite and then take the limit as it goes to infinity. So, when you have a short circuit, saying that resistance is 0 is a legitimate representation, you can use this in calculations. This is correct to say that the conductance is infinity, but you can't use this number in any useful calculation. So, this is a very simple example of why specifying resistance or conductance can be useful, and also you can see why in this particular case only one of them has a finite value. Similarly, when you have an open circuit between 1 and 1 prime, it is an open circuit, the resistance is infinity. So, it is not useful to specify it this way, but you can specify it as a conductance whose value is 0. Okay. So, it means the same thing. Similarly, coming back to these equivalent circuits, Thevenin and Norton, let us take a simple case where between these two we have a voltage source. Okay. So, the entire circuit consists of a voltage source. Again, it could be a single voltage source or it could be the equivalent effect of a complicated circuit. Now, clearly this can be represented with VTH. If this is V naught, VTH will be V naught and RTH will be 0. Okay. Now, if you try to find the Norton equivalent, if you have just a voltage source and you try to find the short circuit current, you will find that the short circuit current is infinity. That is because you cannot short circuit a voltage source, and you will also find that the Norton resistance, which is the same as the Thevenin resistance, is 0. Okay. Now, in this case, this representation is useless because you need finite values. So, only this representation is legitimate. And clearly, by now we would have guessed that if you had only a current source, then you cannot represent it as a voltage source in series with the resistance, because the open circuit voltage of a current source is infinite. So, this VTH will be infinite and this RTH will also be infinite. Okay. So, this is not useful. Instead, you have to represent it as a Norton current source whose value equals the value of the current source I naught and a Norton resistance which is infinite, or a conductance which is 0. Okay. A Norton conductance which is 0. So, you can from this see that you will have to define parameters in different ways, so that you can describe all circuits with finite valued parameters. Okay. So, those are just preliminaries. Now, I will go into two-port parameters, which are basically a way of describing circuits where two pairs of terminals are exposed to you, and you can describe the electrical behavior at those two pairs of terminals with an equivalent circuit. As usual, the internal circuit can be very complicated, but as long as you are given access to only those pairs of terminals, whether you use the full complicated circuit or the equivalent circuit, there will be no difference.